Hi, this is a video introducing a chapter. I'm following chemistry, the central science, chapter 8 on chemical bonds. And this first video is just an introduction to the chapter and just basically gives some definitions of some chemical bonds, the basic chemical bonds, introduces Lewis dot structures and the octet rule. So let's get to it. So what is the definition of a chemical bond? Chemical bond is a strong attachment between two atoms or two ions, for example. And of course, there can be multiple bonds with multiple atoms and ions as well. So there are three basic kinds of chemical bonds. First of all, there is the ionic bond. The ionic bond is where charge is the thing that holds together. So you have one ion that's more positive and one ion that's more negative, and they are electrostatically attracted to each other. That's an ionic bond, where electromagnetic forces are the main thing between them. Then, of course, there are covalent bonds. Covalent bonds are where electrons are shared. And so it's kind of a much more cozy arrangement, if you would, than the ionic bonds, where it's the charge that holds them together. In covalent bonds, you have more of a sharing, kind of a locking of arms. They're more unified. They're very loving and Christian. Okay, then there are also metallic bonds. And this tends to be much more kind of a group effort where one atom is connected to multiple atoms, and the electrons flow more freely in this kind of a group activity. And in that sense, metallic items tend to be more conductive of electricity. Okay, so those are the three kinds of bonds of this chapter. The chapter is mainly going to talk about ionic and covalent bonds. Metallic bonds is a later chapter. So one of the key things to know when it comes to bonding is the octet rule. Octet, of course, if you know a little bit of etymology, relates to the number 8. And so at least so if we're outside the transitional metals, if we're dealing with kind of the heart of the periodic table, we're not talking about the lanthanide or actinide or transition metals, but we're talking about kind of the nonmetals and the metals that are on the sides of the periodic table. Then we have this thing called the octet rule, and the idea is that the valence shell, that is the outer shell of the element, the outer valence shell wants to get to 8. 8 is nirvana. Ah, please let me be 8. Let's get to 8. And so if by sharing or by trading you can get to 8 in the outer shell, that's the ideal for these sorts of atoms, the kind of the heart of the periodic table, the most common elements that we know in chemistry, many of them. So atoms tend to gain electrons or lose electrons or share electrons so that they can get to 8 valence electrons. That is, they try to look like the nearest noble gas. They're trying to become at peace with the world. So that eightness is stability when it comes to the outer valence electron. That's the octet rule. The octet rule says that is for the non-transition metals, the kind of the heart of the periodic table wants to get to 8 in its outer electron shell. And that means it'll look like the nearest noble gas. Okay, so what is the Lewis symbols, Lewis electron dot symbols? Well, they're named after Gilbert Lewis, who suggested a visual way to picture bonding among valence electrons. Very nice, very visual. I like it a lot. So you put one dot around the element. So you take the symbol for the element. Let's say it's beryllium, Be. So you have Be on the page. So you just start putting 1 dot, 2 dot, 3 dot, until you, beryllium I think might be mainly 2. Its default state I think is 2 electrons in its valence shell. So you just basically put the number of electrons that it has in its neutral state, and then it's going to want to get to 8. So if you have something with only 2 valence electrons, it's going to want to lose those so it can get to the noble gas is closest is one that it loses electrons to get to. But if you had chlorine, chlorine has 7 valence electrons. All it needs is one more, and it gets close. Then it looks like it's nearest noble gas. So Lewis suggested you put 1 dot for each outer electron around, and then, of course, once you get past 4, you start to put 2 dots around until you have 2 on the top and 2 on the bottom and 2 on the left and 2 on the right, and you've got 8. And that's what an element wants to get to 8 if it can, which means it's either going to lose, gain, or share electrons until it can get to 8. This is why some elements ionize, and this is why certain elements bond in a certain way. Okay, so here are some examples, and I've you might go top, down, side, left, right, or something like that, but I've followed the way one particular resource I had diagrammed. So if we have a hydrogen, hydrogen has only 1 valence electron. The easiest way for hydrogen to get to a complete outerness, of course, hydrogen and helium they only have 2 spaces in their outer shell. And so hydrogen tends to lose 1, and then it has nothing, which is, I guess, a kind of perfection. So that's why hydrogen tends to go to +1. But anyway, calcium has 2 electrons, so calcium tends to go to +2 because calcium likes to get rid of those. Anybody want an electron? Anybody want an electron? If calcium can get rid of those 2 electrons, then its valence shell becomes the next lowest down, which is full. And so calcium tends to become +2 by giving away 2 electrons, so it can get to its octet rule. Carbon is right in the middle, and of course has 4 valence electrons, which is why carbon tends to form, CH4, C2H8. It tends to form covalent bonds with multiples of 4 because it has 4 valence electrons. Oxygen, as you can see here, has 6. So oxygen tends to want to gain 2 electrons to get to 8, which means that oxygen tends to be -2 when it goes into an ionic state. Chlorine is very close to 8. It only lacks 1. And so chlorine often will gain an electron and go to -1. So you can see how the octet rule, if you don't understand it, it's okay because you'll have some practice. But basically, the octet rule says that it explains why certain elements go to a certain ionization charge, and why they share a certain number, tend to share a certain number of electron spaces with other atoms. So that's the introduction to the chapter. Of course, much more could be said and will be.